Okay, good afternoon, gentlemen. There's no lady in. I welcome you to the third session on microacoustical transducers. Today I will make you familiar with fundamental principles of MEMS microphones. And so still I talk about history of MEMS microphones or microphones in general. And later we jump then to the MEMS microphones. In the history, we see something about the basic principles. I introduce you to some general transducer ideas. And one of the first successful microphone, which is really small, was the electret. So we see this, and then the change to the silicon microphones. And I reflect on the sensitivity, how to define this, and what is important to gain it. There's a limitation in as well, which is the so-called pull-in effect for electrostatic transducers. And we see the compliance of diaphragm, which is also quite important. And last but not least, a little insight into business topics for those devices. Okay. So history of acoustic transducers. Yeah, if you want to transfer audio information about a longer distance, we need to understand what is important. We had this in the past already, that in the free field, sound is degrading over distance. It's proportional to 1 over the distance, sure, because we radiate into space. We lose a lot of energy over distance. That means if you double the distance, you lose 6 dB in sound pressure level, which is 1/2. Or if you have 10 times the distance, you lose 20 dB of signal. So if I'm talking like this with a sound pressure level of maybe some 60 dB, and we are 40 meters away, so you couldn't hear me anymore, because then it is dissipated in space and it is on the noise level. And for this, people have always been seeking for chances to transfer sound over longer distance. And the question is, how could you do so? And I have this nice example from Smithsonian Institute Museum that found in their store facility this device, which is 1,200 years old, from the Chino Indian culture in North Peru. The two beakers with a diaphragm at the end and a 25-meter long wire in between. So if you pull this straight, you can use this like the kids have been doing in the past. Or I tried this also. You have two cups, and you pull a wire tensioned in between those bottoms of caps, then you can transfer sound this way. How does it work? Very simple. If you talk into this cap, the bottom is vibrating, and the wire transfers this longitudinal vibration. And since it is one-dimensional, the wire has only the intrinsic loss of the material. So this way you can transfer sound over longer distance without a lot of degradation. And this, of course, the mechanical principle of transferring sound. Good, well understood, but forgotten, and not really a technical use to implement this. So then we see here the intention from Philip Reis, 1862. Mr. Reis, he tried to study the human ear and how it is working, and want to basically record sound. And what he did, I wouldn't say naive, but he imitated the human ear. A lot of effort in structuring the outer ear from a wooden device, and he puts a diaphragm from a sausage behind the ear. He's missing the ear tube, and trying to modulate from their sound. And this diaphragm is connected to a hammer, kind of a device, which is this movable joint here, anchored on a pivot, and it is screwed behind the ear. So one tip is connected to the diaphragm with a wax. And then if the diaphragm is moving, it is transferring the movement outwards with this metallic device. So then the end of this wire is connected or is touching, simply touching the end of another metal piece. And just by vibration, it makes contact or opens and closes. So it is kind of very simple modulation with a contact. And then basically you could adjust a modulated current through this device. And this is a very, very simple demonstration of a human ear or a microphone modulating current. So yeah, there's a biography where you can read all these devices and trying to understand how human ear works and how to make this for technical implementation. And this is then basically his first telephone, where he imitated, okay, he didn't have this ear anymore, but he has a bigger diaphragm, and you see on the diaphragm that metallic contact and the needle again. And if you speak into this funnel, the volume is vibrating the diaphragm and modulating the current. And if you do so, you attach wires and of course battery, and you have a second device at the end of the electric wires, which is an electromagnetic device, which is starting to vibrate in this direction and getting this vibration to a wooden device, and this is emitting the sound again. So this is the way of having one-way acoustic electrical transmission. And if you look at this, if you had like the velocity of the diaphragm, you have only in the upper spot, in the upper maximum, a contact. This is kind of a very bad modulation scheme, but it is enough to simply hear what is spoken. But of course, not very good is kind of a Nyquist limit of this transfer. Yeah, so the telephone was invented in the 60s of the 19th century. And what I put in here, it is somehow kicking off a lot of inventive ideas how you could generate a microphone and from there have an electrical transmission of signals. There's times when anyhow electricity came up. So the idea of communication. So Elisha Gray, he invented like a contact or a fluidic microphone at a diaphragm with a needle below, and the needle is peaking in the conductive fluid, and depending on the distance or the contact area of the pin into this fluid, it could modulate the current, simply a current modulator. And of course, it's not very practical because liquids move and you cannot make sense out of this so much. Then was Siemens, yeah, had a patent those times for a magnetoelectric apparatus. Already a quite complex situation. He has a magnet, the two poles of a magnet joining with a yaw, and into the pole gap he puts a cylindric coil, and the coil is of course moved by the sound on the diaphragm. This device is acoustically driven, and then of course while moving in the magnetic field, the current will be modulated, and this is a first electrodynamic microphone. Those times machining was not very precise, and he had this tuning device, so not easy to generate such a device, and for sure nothing which you can do in high quantities, very delicate situation. But electromagnetic transducers we still have today for the speakers, more or less the same way. Then Graham Bell, and we know the Bell Labs, he invented an improved telephony, and this also something we find still today in classical microphones, the electromagnetic transducer using a microphone, and on the other hand side a speaker. Again, simply a moving armature. So basically there's a electromagnetic one coil, and a yaw is moved against this and modulating the current. And the inverse, because it is of course inverse, is on the speaker side, and this you put to your ear, and then you hear the sound which is generated, or the mechanical movement of this diaphragm, which is transferred via the wires. So again, something, and the balanced armature or armature devices is still nowadays in hearing aids, for example. And last but not least, Edison. So we have all the famous inventors of those times in this field. He is doing also telegraph, and he invented a carbon microphone. What is a carbon microphone? Carbon as a powder has some resistivity, of course, and if you compress the powder, the resistive is low, low, because the powder is in better contact to each other. If you then put the powder in such a box with a contact on the one hand side and the other contact modulated by a diaphragm, then you modulate the current of the resistivity of the powder and modulate the current this way. So different ways of modulating current, all busy in the 70s of the last century. Quite interesting. Everybody was keen, like a hype situation those times for the telephony. And yeah, finally, some 20, 30 years later, we have an invention of Mr. Vente, and he invented a capacitive microphone. So, and if you look at the device, it's just a cross-section of his patent. He has a metallic cylinder, which is supported by a glass device, so insulated. And this is connected into one part of a mechanical device and is screwed to a second part. And in between those two halves, they clamp a metallic foil. So here you see that you clamp it, and then you have a little gap between the two electrical conductive devices. And this is simply a parallel plate condenser. And if you move the diaphragm with the sound, then you can modulate the capacitance. So this is the principle that we still use today for capacitive sensing. And why could it be successful those times? Because they invented the vacuum tube, I don't know, somehow in the same times. And with the vacuum tube, you could pick up the capacitive of the microphone, which is very high ohmic. You see here some 20 mega ohm bias resistance in between. This is the biasing of the condenser. And then they pick up the tiny signal from the change of capacitance and amplify with the tube. And the tube is finally the enabling technology for microphones. And then you have a system which is, which you can transfer then over longer distances and be able to make telephones out of this. So basically we are more than 100 years back and had already the basic design of a capacitive microphone. Yes, and okay, I come to the 70s of last century, and this is something of condenser microphones that you still find today, those luxury von Neumann microphones. I couldn't call this a micro. It is 2-inch, 2.5 centimeters diameter. That is basically the diaphragm that is inside the system. And if you open such a housing, you have a vacuum tube below, and it's still amplifying the signal and biasing the diaphragm. And those high-end microphones have very, very good signal-to-noise ratio, so they're high-quality devices, and still manufacturers. The focus is on manufacturing, because if you see here the construction of such a device, you have an insulated back electrode and metallized diaphragm on top, and you see how they do the metallization. So they have a metallized center area of this diaphragm and put really the connection to this tiny diaphragm with a screw and a wire to the outside. Very delicate, and then with screwing the screws on the frame, they control the tension of the diaphragm. Of course, this is a quite sensitive device, also a very expensive device, but still musicians, artists, they use these devices very favorable. Yes, and out of this time also we find reference microphones still commercially available. You see, this is the company Brüel & Kjær, for example, their portfolio, a lot of capsules. These capsules are all capacitive transducers after the principle of Wente. And if you look inside the construction, you still have this plate, back electrode, which is on a glass connector. And here you have a counter contact from the amplifier, which is connected to the back side. And by screwing a metallic foil is tensioned across this back plate and have a gap of maybe some 30 micrometer. And this you get for calibration of audio setups, or in wherever high level measurements are done, you find those devices. And it's still available today. Yeah, it's quite interesting to see this movie. I connect to you, I can share this. Hope you is running. This is the manufacturing that they apply today. Everything semi-manual. There's the foil spun on the device. This is crazy. With a weight, they control the tension finally. This is the back connect with a spring contact. There's some galvanization maybe. Lithography. A reflow oven to temper the device. Optical inspection. You see they do this in a clean room. Particles are for sure bad in here. Then it is connected to each other. There's an acoustical test or a mechanical test. Yeah, there's mechanical testing. Huge number of processes, and this is crazy. Cleaning the diaphragm before you assemble it, and then it's connected to each other. Capsule is ready. Audio testing in a closed environment. There's a frequency response. The voltage testing is the protective cover. You can see the final video test. And then I sell it in such a device. Okay. So just to share the complexity of fabrication, if you do those kind of devices, must be expensive only from there. Yeah, what is important to do if you want to design a microphone? And we are not yet checking how to transfer the signal, first of all, we check on a diaphragm that is moving in a sound field. Basically, you need a compliance of this diaphragm. It must move in the sound field, and finally you need then to pick up the movement of this device. So if you have a pressure field like this and a membrane just in the pressure field, it is wrong, this situation. It wouldn't move because the pressure on both sides of the diaphragm is the same. All audio frequencies are long, and with respect to a diaphragm, it is like an isotropic pressure field. So this couldn't happen. To make this happen, you have to have an enclosure. So you have to encapsulate a reference pressure. So this pressure is some standard reference pressure, and then the change in pressure outside will deflect the diaphragm in one direction or the other. So this is necessary to have this encapsulation. Last but not least, if you have this encapsulation and you would change temperature, for example, then if you heat up, the volume could not escape and it would blow off the diaphragm in one direction or down. For this, you always need the pressure equalization hole in your package somehow. Also, if you would have this box of a microphone with a diaphragm and move up and down, the equivalent pressure change over height is around about 1 Pascal over 8 centimeter height. This is a typical situation, and 1 Pascal is already high sound pressure level. So if you would move it without this equalization hole, you would have an equivalent sound with respect to change of altitude. So this is the reason for always having some ventilation hole inside this system. Later on, we will discuss about the dimensioning of this ventilation. Yeah, and this makes basically the microphone. Finally, you have to find how to measure the deflection of diaphragm. And we saw before that we can do this capacitive, but there's so many ways of doing this, and we have discussion about this. Now the next question is about the dimensions of those systems. What is meaningful if we want to get small? So yeah, and we have to know about what we discussed in the past, that we need somehow, or we would like to have an impedance matching to the field of the impedance of the characteristic impedance of sound. So Z0 being 412 Newton seconds per meters cube. And if you have a different impedance of the microphone, which is basically the diaphragm, we'll have a reflection. So only if you have a perfect matching, or we would transfer most of the energy, or at least 50% of the energy in the matching case from the sound field to our device. And the question is whether we can achieve this minimum reflection or zero reflection or 50% of energy transfer for such a microphone. Then we would be king in terms of microphone design. Now we try to make an estimate. So if you had a microphone with a diaphragm of 1 millimeter square, this is a realistic dimension for a MEMS device. Then we would have to meet the impedance Z0 over 1 millimeter squared, getting the acoustical diaphragm impedance of 412 10 to the 6 Newton second per meters fifth. Crazy dimensions. Nevertheless, so this is the impedance to meet. If I have such an impedance, I can calculate back the compliance of a diaphragm. So we have a pure capacitive or compliance here of the diaphragm, so no losses, no inductance. We simply calculate the diaphragm compliance from here, ending up in this number 4 times 10 to the minus 13 meters cube per Pascal. And this acoustical compliance, if you divide this again by the diaphragm area, we get the specific compliance, which tells us a little bit about the displacement of our diaphragm. So it would end up with 400 nanometer per Pascal displacement. This doesn't sound so bad. 400 nanometer for a diaphragm, maybe, which is a micrometer thick or so, is feasible. Only if we look at this, if you have high sound pressure levels, like this 120 dB sound pressure level, this is some very high limit, we would displace our device by 11 micrometers already. So this is for a 1 micrometer thin diaphragm, only 1 millimeter in diameter, a huge displacement. Not sure that we can make this, but okay, we have this. Now this is a pure compliance of the diaphragm, but now we see that we have this enclosure, the package, and we want to make this small as well. So we assume that we had a volume of 10 millimeters cube. So then you have 1 millimeter diaphragm on a 10 millimeter cube volume is a feasible small dimensions. We calculate the spring or the compliance from this cavity as well, because these two compliances which are competing with each other. So the spring of the diaphragm and the spring of the back volume are sharing the energy. So we would need it in a similar dimensions. Okay, calculating from the volume divided by rho and c square, we get also a compliance. From this we can calculate basically the acoustic impedance of the cavity, resulting in 2010 to the 6 Newton second per meters cube. So now the impedance of the cavity and the impedance of the diaphragm is quite different, so a factor of 5 in between. This means that basically in this situation, the impedance of the cavity is dominating. So I have a soft membrane and a stiff back volume. It doesn't make sense really. So I cannot make use of the compliance if it is limited by the impedance of the back volume. So impedance matching is from there quite difficult. So then we can do something else. We can match the diaphragm to the volume of the cavity to at least have here a fair situation. So then we get still some reflection. But look at this, if we get now our diaphragm compliance the same from the same impedance like the back volume, we end up with a compliance of 70 nanometers per Pascal. 70 nanometers per Pascal is then the sensitivity of the diaphragm. And I check again for the upper limit, 120 dB SPL sound pressure level. It makes a displacement of maximum 2 micrometer. So this is still a lot for 1 micrometer diaphragm typically, but still feasible. And so we allow for some lower sensitivity to get the dynamic range and be matched to the volume of the cavity. This is a typical way of designing a microphone or trying to match situations. We see we have limitations, but also chances. Yes, so a lot about compliance then of the microphone. And as I said, jump over this, we need to sense finally the displacement of our diaphragm. And just to go through physical principles, we had seen the capacitive transduction principle, and there's a lot of distance, different situation, the plate distance, but also plate overlap or piezoelectric devices. These all kind of capacitive transducers, which we can check. And it's also always interesting, they are reversible effects. So you can use it the one and the other direction as a transducer, not only microphone, but maybe later on also for speakers. Then of course we have the magnetic transduction, voice coil or balanced armature. We will see something about this as well. So these are basically reversible effects, but then there's also irreversible effects like resistive change. We know the piezoresistive or magnetostrictive principles. We can use this to measure tension or in a diaphragm which is moving. With thermal effects, this is a totally different idea. We are talking on the left-hand side always about diaphragm displacement. Of course, there could be non-diaphragm solutions to measure sound. but this very special idea basically would sense the density of air which is fluctuating. With optical means, you also have quite good chances to measure deflection of devices, maybe by inclination with lasers or in resonators like Michelson or Fabry-Perot resonators, or with waveguides. Finally, also quantum effects are available, like field emission or tunneling joints that measure little displacements. So there's a lot of principles that might be used, and we will see some of them being implemented. Still, most of the time, the capacitive transduction principle is used, and we go a little deeper into this and what it means to sense a capacitive microphone. Yes, okay, we are back to some historical ideas. Back in the 60s of last century, Gerhard Sessler and Jim West, they were experimenting about cell transducers. This is something that you have in headphones. And they wanted to make headphones in the Bell Labs in the US that sound good and transparent whatsoever. You have special effects. And for this reason, they use an electrostatic transducer. So with high voltages, they move a tiny foil. The foil is metallized and has basically the electrostatic transduction principle. And they did so, and to drive such a system, you need high voltage, let's say some 100 of volt, to move then the foil in your headphones. And they discovered if they tested the headphone the first day and the next day and later on, the sensitivity of the headphone was changing. So it was not so sensitive after you used it for a while. And they didn't know, or they had to find out what is the reason for that. And finally, they found that in the metallized foil, there was charge stored. So if you have polarization voltage on your metallized foil, you influence charge into the foil, which is giving rise to charge dissipation. And then it is building up a counter field, and this is reducing the sensitivity of the headphones. And then they said, okay, we can use this foil also to make a microphone out of it. And they invented the so-called self-biased condenser microphone for high capacitance. So this is basically the sketch of it. They had an electrode and then their special foil, which could move in the sound field. And since it was polarized, it would give rise to charge dissipation or charge movement, which you pick up finally in an electrical signal. They called this electret. This is an artificial word, so to say, coming from electrostatic and magnet, because they had the feeling they have a permanent electrostatic field, like if you had a magnet which is always giving a magnetic field. So they were delivering an electric field out of their foil. So the foils are kind of Teflon foils. And nowadays, if you do so, you do a corona discharge situation. Basically, you have an electrode and the foil on top, and you polarize this for tens of kilovolts, for example, and then you get into your sample this charge dissipation. So the metal film may be positive, and the dissipated charge in the foil, which is then more or less immobile. And if you did this charging, you put out the foil, it is keeping the charge dissipation. There's only one drawback. If you heat such a device up, such a foil, maybe 80 degrees C or higher, then the charges get mobile again, and they would cancel each other again in the system. Or if you have high humidity, then the humidity gets into the foil, is getting also charge mobility, and then it could degrade. So we have to keep in mind that these electrode foils are somehow sensitive to environment. So this is the way of getting this foil, and then you're building up a microphone. How does this work? Either you have really this electrode foil as a movable device and a second electrode, building up this condenser. And what nowadays is done, you put the electrode on the counter electrode, which is stiff, and you have simply a metallized or a metal foil moving against this. You do this because the electrode functionality and the mechanical functionality optimizing at the same time is maybe not so easy. If you look then at the electrical situation in this device, we have a capacitance from this electrode. Electrode maybe have a dielectric constant of 2 or so, yeah, and we have a field in the gap between the electrode and the counter electrode. The total charge is constant in the device, so we get basically the same charge on both of the electrodes. And from there, we can finally calculate back the polarization voltage, which is given to this device by electric field, which you get from the electrode and the distance of the gap. And you can calculate from there the specific voltage on my device, which is given by the electrode. And I have a simple example. Nowadays, those electrode microphones maybe have some 3 millimeter of diameter. The gap is maybe 10 micrometer, and PTFE foil is also something like 10 micrometer thick with a specific charge per area included. And this from the calculation gives some 36 volts. So I have 36 volt over 10 micrometer air gap. And this is somehow feasible. And we see there's not anymore these 200 volts from the big capacitive devices. But if you go for smaller gaps in this electrode, we still get a fair polarization and voltage. The nice thing of these electrodes, they don't need an external biasing. Yeah, you have an included biasing, and this is basically the invention. And from the 60s of the last century till the early 2000 years, this was the device which is in each telephone and each audio application, because it could be cheap and manufactured in millions and billions of devices. Yeah, this is how they are fabricated nowadays. This is from cheap toys. You'll still find this kind of metal can with 2 connects to the outside, and inside you find here the diaphragm span over the electrode on a back plate in this metallic housing, and quite often there's an IC or a JFET and a transistor which is transferring the signal, the high impedance signal, to a low impedance for the outside. We talk about this soon. And this is simply the cheap devices that is maybe cheaper than any MEMS microphone, but is also limited and has a lot of drawbacks. This, by the way, is an electrode capsule from 2010, and this is basically the miniaturized version of it. And just to show you, this is a Nokia phone that is still alive, and I still have this in my drawer, but I don't use it anymore. This is the port where the microphone comes in. If you disassemble this, you find the microphone mounting. It's like a plastic device with some spring contacts. And just to show you how this is applied, I put this out. Here's the sound coming in. This is a rubber device, a metallic device. You see here 2 spring contacts. Why spring contacts? Because if you solder it, you go to 200, 300 degrees C, and you would degrade the performance of the microphone. You put this double spring contact off, you find the cylindrical capsule inside, and this is basically the microphone then with 2 contacts. And if you put it together, it's still working, as I said. So this is electrode microphones, and you see how complex it is already to assemble this and to connect it. It is for sure expensive to do all this manufacturing, and this is a reason, for example, to move to modern microphone technologies. And you find still nowadays a lot of high-end electrode-based microphones with different form factors. typically with this tubing, which you use in in-ear devices or hearing sets. And nowadays, again, you find those devices also in in-ear phones. So this is something which is specific. And you see here, you get into this spout, into this hole, you transfer the sound into this front chamber. And this tiny device here is the diaphragm. The green one is the charged backplate. And this is the way the membrane is moving then. And the inner volume is the volume then which is in competition with the compliance of the diaphragm. And at the same time, you put some electronics into this volume to read out the signal. You can see this is a very complex construction, and they are quite expensive, those devices. Yes, so we see all these classical microphones, which are famous. The silicon MEMS microphone idea, again, came from Gerhard Sessler, who invented these electret microphones, or was co-inventor of this in the 80s, when he came from the Bell Labs to Germany, University of Darmstadt, or those time Technical University of Darmstadt. He was trying to follow up in the MEMS transduction principle and invented then the silicon process for microphones. And those times he simply put in his patent this kind of a construction, a silicon base with some dielectric spacing and a metallized diaphragm on top of this. And then you see you have two electrodes with an air gap in between. And if you polarize this, you of course have kind of this capacitive transduction principle. And he also put in this reference volume from a housing, for example. So this is a long time ago, nearly 40 years ago, when silicon MEMS microphone was invented. And if you look at this slide, you see how the share from MEMS microphones changed over the last 10, 14 years against the electret capsule microphone. So begin 2000, there was only known the electret capsule microphone. And already, if you know, some 20 years of research on MEMS microphones, but still in those times, the MEMS microphone came to market. And then it changed completely the situation in those decades. So the MEMS microphones were in favor. If I at those times, or early those times, was advertising the MEMS microphone, I was arguing about the advantages of MEMS microphones against the electret microphones. Yeah. First of all, I can always argue that the silicon transducer, however it is made, it will be temperature stable and humidity insensitive. So it will be a robust device. And then, of course, if it is in silicon, I can do batch production, not device after device, but I have thousands of microphones on a single wafer fabricated. That allows a better production control and the tight matching of sensitivities, for example. Yeah? And those have the spring contacts. The silicon microphone has SMT capability. So you can put it on a PCB, do the reflow soldering like any other electronic device. And then the argument is we could get smaller in form factors and so on and so forth. So I could argue a lot about those benefits, but customer was hesitant to take over. What you see already, those capsules are cylindrical and have special construction, but the microphones have totally different, the MEMS microphones, totally different form factor. And if you jump from an existing well-established technology to a new one, you have to, you run a risk. You will see that, okay, what if the microphone will fail? It is a MEMS, all those brittle, tiny stuff, can it be last long and be stable and stuff like this? That was a good debate over there. So they asked us, can't you do a form factor which is similar to the electret capsule? It will be risky. But somewhere in time, it was here the phone from Motorola, the Razr phone, this flip phone. in 2004 came to market. And when they planned this microphone, this telephone, there was the company Knowles, which is also in Michigan. Yeah, they did the development of the very first MEMS microphones in those new form factors. They were in close contact to Motorola, and Motorola said, okay, we try this new form factor. We are not sure that it will be successful in the market, because before all the phones were only this kind of brick type. They didn't believe in the success of this phone. And they said, okay, we can risk to put a MEMS microphone into this telephone, because if MEMS microphone is failing, we don't risk a lot of business volumes. So they fabricate this with a MEMS microphone, and it was not expected that this flip phone was so successful. It was selling like hell, and the whole market wanted to switch to this form factor and found this so sexy. And then the demand for MEMS microphones was high at this starting point, and Motorola was seeking for a second source, not only the one who could fabricate. And then, for example, Infineon jumped in and also served with these kind of microphones. So you see, then by this good chance, the market was opened, and the trust could grow on the technology of a MEMS microphone. And this basically was the start of these MEMS microphones into telephones. And then you see more or less a complete change in the market, the benefits, the performances were growing and working against the electret capsule microphone. So this is basically the story, or the starting story for these new devices. Yeah, so what is inside? Inside this device, you will see this transducer, the capacitive transducer, and we check a little bit about this. It's a very simple construction, top level, but the specific ones are then in detail. You have the red one is the diaphragm, which is made of a conductive polysilicon typically. This has the compliance, moves in the sound field, and has a tiny hole in, which is the air equalization hole, what the ventilation hole, how we call this. And the air gap is maybe 1 to 2 micrometers. And then you have a static backplate, also conductive, with a lot of holes inside. The holes allow the sound to transfer through this plate and moving the diaphragm. And of course, this is all fabricated on the substrate, and the substrate needs a hole below the diaphragm, else it couldn't move. Yeah. So, and then you have basically this parallel plate transducer, which changes air gap over sound pressure. And from there, we develop then the whole microphone device. So very simple, how to drive this condenser. We go through this. We have this capacitor, change the gap distance. The question, how is the work changing, the electrical work over this? If you displace by a delta X, we can derive from the charge on the condenser, which is changing. If you displace the diaphragm, we have two formulations from this. One is proportional to the voltage squared, and the other is proportional to the charge squared. And the question is now, how do I bias my device? I have two different chances. I can give a constant voltage across the condenser, or I can give a constant charge on the condenser. And respectively, the force on the plates behave differently. So if I have a constant voltage source to my device, I can then derive the force on the plate by differentiating the electric work over the displacement. And I take then for constant voltage this formula, and no wonder it is 1 over x. I get the squared version. So I get a force which is nonlinear over displacement. Of course, it can be very sensitive, so we have a lot of change for small displacement. This would be nice for a microphone, but the nonlinearity also is risking stability And if we want to transfer sound, somehow we don't expect nonlinearities because they end up with, for sure, a bad sound impression from there. But if we instead use it with a constant charge biasing, so the voltage could change then. I take this formula and capacitance is a denominator, and we have then the x in the vice versa. We differentiate over x, and we get then a linear or a constant force for the parallel plate system. So you change, you modulate your diaphragm, you displace it, but you always have a constant force on the plate, and this makes a less sensitive device, but a stable device for sure, because it cannot collapse this way. So this is the way how to do this, but how can we apply constant charge to a microphone in the microelectronic world is, okay, we see later. Just a remark, if you had the chance not to keep the distance of the plates constant and do the overlap change, there's some kind of other transaction principle. So if you do this change, then of course the situation for constant force and constant and variable force will change. Basically, then you have capacitance proportional to the area, and the area is inverse to the distance. Basically, the situation will change. You would have then to apply constant voltage to your device to generate constant force with modulation. Okay, back to the constant charge parallel plate distance changing devices. How to generate this? Basically, this is the typical situation how we do the biasing and the amplifier situation for such a device. This is called high ohmic biasing. Basically, we have a voltage source which is biasing the condenser over a very high ohmic resistor. High ohmic, maybe we have a resistance of 10 gigaohm and maybe a capacitance of 3 picofarads. And if you switch on here, there's a charging of the condenser, but the charging time constant is very large, or vice versa. The corner frequency of this RC filter in this case is some 5 Hertz. So it means if I change my condenser faster than 5 Hertz, it will generate a voltage swing on this node, which can be amplified. And the charge has no time to relax or flow into the bias again. Yeah. So this means we can modulate this node with frequency higher than the corner frequency, and this way have a transaction principle with a flat response higher than the corner frequency, and with lower frequencies it is degrading because then we have a charging and discharging of the device. So this is a quasi-constant charge biasing, and if we design the corner frequency so low, it's anyhow below our audio bandwidth. So maybe we want only to transfer 20 Hertz to 20 kilohertz, and then this is a very fair situation. It's only that, yeah, I said already, the charging time is 200 milliseconds. So if you switch on your bias, it will last 2 eye shots to charge it up. This is something which you have to take into consideration. And yeah, how could you arrange this in nowadays solutions? This amplifier, nowadays we use CMOS technology. In the past, there was junction field effect transistors, for example, like this. And here you have a gate source diode. The gate source diode has, in this situation, reverse biasing, but always this diode has a leakage, and the leakage is basically representing this high ohmic resistance. So you charge your device via this leakage path of the transistor, and then you can transfer the signal. This is basically used also in the electric devices. Or you do a special biasing point by antiparallel diodes. So this is typically done in CMOS technologies because the CMOS transistor, which is basically the impedance transformer from this node to the outside, it has no leakage. It is an oxide gate, so it doesn't leak at all. So you need always to find the right electronic solution to it. Yeah, the advantage of this, it is really low power supply. You don't need a lot of, it's quite easy to implement and simply straightforward. Okay, this is very basics on charging condensers, and now we go back to discuss about the sensitivity of the microphone. Yeah. So we need to deliver a certain sensitivity to read the microphone. And of course, we can talk about an electrical sensitivity, which is simply the change of voltage over displacement. Yeah. And this change of voltage over displacement, basically we have the charge and the capacitance. And if we derive this over displacement, we get the total charge on the condenser divided by the area and epsilon zero. Yeah, this is equal to the bias voltage over the distance of the gap. So to get a high electrical sensitivity, we should charge it to a high bias, or vice versa, we need a small gap between the electrodes. So if you want to run such a device with a battery operation, like 3.6 volts is a two-cell situation, then you should bring up a very small distance. And if you remember the electrode with 36 volts at a 10 micrometer gap, we see already this is not really CMOS level. It's not what you typically apply in your cell phones with 2 or 3 cell applications. Okay, this is the electrical part of sensitivity, and the mechanical sensitivity is simply displacement of the diaphragm over applied pressure, which is the acoustical compliance of the diaphragm over the area of the diaphragm, or we call this also the specific compliance of our diaphragm given in meters or nanometers per Pascal. So to get the total sensitivity, we have to multiply electrical and mechanical sensitivity, and then we see, okay, we have the bias voltage, the distance of the gap, and we have the compliance of the diaphragm divided by its area. So we get the volts per Pascal sensitivity. And yes, large bias, small air gap of the condenser, and large mechanical compliance of the diaphragm. This is what we need to generate a sensitive and good microphone. So biasing we discussed already. The new thing in MEMS is generating compliance, and we can discuss this. Yeah. But before we go into really the compliance of our diaphragm, which is basically the sensitivity effect, we check about limitations, electrical limitations again. Basically, how large can a bias voltage be if you have this spring and situation? And basically, we could sweep the bias on an existing microphone higher and higher and higher. So we generate an electrical force about our plate, which is again proportional to the bias squared. So we run this situation. So we run electrical force higher and higher, but the spring constant or the compliance of my device is constant. So for sure, there will at one point be an intersection of the two forces. And if you run over this point, the diaphragm will collapse, or the electrical force is so high that the membrane will collapse. Collapse means it hits the back plate and then it's not functioning anymore. So we call this the pull-in voltage. We want to derive at which voltage we have this equal point. And then afterwards we say, okay, we need to respect our design below the pull-in voltage. So whatever we bias our microphone, it must be with a certain distance against this critical point. Yeah, and we can find this critical point with an energy equation. So potential energy is equal to the electrical and mechanical energy, which we can simply write in this formula. Then we check for the net force being 0 at equilibrium position. So we derivate the energy over x, and we get the forces and set this equation to 0. And this basically gets us the critical pull-in voltage at the point where the system is collapsing. And from there, we get an indication for the displacement at the point of pull-in. And we put this in again into the formula. The change of force over x can set this 0. This is exactly the point where we have this equal point, and we get out the displacement is 1/3 of the gap that we have. So if the membrane is attracted to say 1/3 of the total or initial gap, then we have reached the pull-in voltage, and then the system will be unstable and collapse. So finally, with this information, we can formulate the pull-in voltage to be 8 times the distance to the third, divided by, and there's the area and the compliance or the specific compliance of the diaphragm. So pull-in voltage depends inversely to the root of the compliance of the diaphragm and the specific air gap that we prevent to this device. So this is a side condition to the design of a microphone, which is limiting the sensitivity of the system. Yeah, this is just an example of a measurement, because if you look again back to this here, the pull-in voltage is a sudden event. So basically, if you do this under a microscope, and I give you an example of this, you can see this, or you can even measure it electrically. So if we measure the pull-in voltage and we had the air gap from the construction, we can then back calculate the mechanical sensitivity of our device. So there is in this formulation, in this idea, already information about the sensitivity of our MEMS device. And this is just another kind of measuring it electrically. You have the voltage over this condenser, and there's just a cross-section of such a microphone. If you run up the voltage, the diaphragm is displaced. At the pull-in, it is hitting the membrane. And if you increase the voltage further, then the membrane is ever tighter, clamping to the back plate. And this is exactly this capacitive measurement. So at 0 volts or at low voltage, we have some 4.8 picofarads capacitance. We see if we get higher in voltage, the capacitance is increasing only slightly, only little. Then at the pull-in point, we have already quite some significant air gap change. So the capacitance has increased, but at the pull-in, it is jumping suddenly till it is hitting the back plate. And of course, if we further increase the voltage, here we see how the capacitance is increasing because they come closer and closer in the area. So this is typically a situation in a capacitive measurement. This is a measurement, no, come on. Yeah, this is an optical measurement of such a diaphragm. In this measurement, you see that we run up the voltage and now down again, and the diaphragm is moving. The backplate is transparent for this measurement, so you won't see this. I run it again. You see the voltage is increasing. Zack, now it is hitting and moving again, and now we reduce the voltage again, and it's getting free again. And now a little free oscillation of the rest of the diaphragm. So this is also a way to detect pull-in, and yeah, what you can do with this is an early measurement. We plot basically the sensitivity over the pull-in voltage that was measured, and we get again this squared relation. One test of theoretical curve and some measurements, a lot of different devices, never hitting perfectly, but you get this relation. And last but not least, we see here a fab measurement. There's some 1,000 microphones or different lots fabricated. And we see here the sensitivity in decibel volts per Pascal plotted over the pull-in voltage. This scale is hidden because it's production data. And you see here that we have a straight correlation between sensitivity and pull-in voltage, which is basically reflecting here, reflected in this formula. And last but not least, we want to extract from the given gaps and measured pull-in voltage, finally, the compliance of our diaphragm. Because if you measure in the fab simply the MEMS, the mechanical device, you cannot measure acoustical sensitivities, but you have to deliver to your customer if you sell such a wafer. So we need basically this formulation of pull-in measurement versus sensitivity. And there's a good correlation in between. And last but not least, the claim is that people use only 60% of the range of the pull-in voltage. So if you have 10 volts pull-in voltage, you do the bias maximum to 6 volts to have quite some spacing against the limitations. Yeah, and since we have this limitation always in our systems, there's a lot of optimization in between. You could keep basically the bias voltage constant, say 2 volts or so, and then you increase this green area, you increase the compliance of the diaphragm, try to achieve more sensitivities, and but you have to respect that you never should do more than 6% of the pull-in voltage biasing, and then you can run up in the sensitivity. Another way is trying to change the gap distance between here 1 and 2.4 volts. So it's a way to find optimum sensitivity. It ends up to something like 25 millivolts per Pascal sensitivity of such a device. Or you can vice versa say, I always put my sensitivity to the maximum of 60% pull-in voltage, and I allow for biasing less than 2 volt, but variable biasing. And this is the other way of optimization of the system. Basically, it runs to the same point that you want to have not the biggest gap and not the highest voltages, but you run always in this field of optimization. Not maximum compliance of the diaphragm is the best always. Yeah, but what is compliance of diaphragm? Have a look at this. We have different types of diaphragms to discuss. Everybody knows basically a membrane, which is basically a circular tiny device, tensioned, so you have tensile stress inside and clamped all around. It's like a drum, yeah? So it can move, but you have a high tension inside. You get the cross-sectional displacement of this diaphragm with respect to the diameter or the radius of your device, some squared behavior. And finally, we get out an acoustic compliance for such a system, depending on the diameter or the radius, of course, is inverse and linear inverse to the thickness of the diaphragm and linear inverse to the stress inside my membrane. So if I have a high stress in my membrane, the sensitivity gets lower. And if I reduce the thickness proportionally, I get higher compliance. This is scaling parameters, of course. So people have sought to do diaphragm without stress. Then we call this a plate. So if you have a circular all over clamped diaphragm, which has no tension, so it's just getting bending, then you get respective compliance, which is inverse proportional to the third of the thickness. So if you halve the thickness, you 8 times reduce your compliance. It sounds like if you can make this, you can generate very sensitive diaphragms because the parameter thickness is a good chance. But keep in mind, if you have variations in thickness due to production, you also have variations in your mechanical compliance. So this is always trade-off finally. And then finally, there's a third version, which we call the floating plate. It's basically, again, a plate without stress, but it is not rigid, fixed to the support area. It is basically sliding on the support. It's free, and it's just a free moving or displacing plate. You have basically more or less the same behavior, just the quer contraction is still in here, and it's also a good chance. Why is it maybe the better chance than the clamped plate? If you have a clamping situation and you have compression from outside to your device, it will generate compressive stress to it. Or if you have tension, you include some stress to your device. If it is floating like this, it cannot react on external forces. So you have always ideally free floating plate. So with this set of mechanical devices, we have diaphragm chance to transfer sound. Some simple discussion. If you have mechanical compliance 10 nanometers per Pascal in the center displacement, that means 280 nanometers peak displacement at these very high sound pressure levels, which we want to achieve finally. So this is a feasible situation. This is something we want to finally have. And we have here just the displacement form of membrane plate and floating plate. We see already, okay, over the radius, the floating plate effectively has more displacement over the area. So if you have a capacitive transducer, basically we want to have two plates moving parallel to each other and not the center moving a lot and the edge a little. This is not perfect for a capacitive transduction. And for there, maybe there's an advantage for the floating plate. What we do if we compare the sensitivity, or if we simplify our measurement, we calculate the equivalent piston displacement. So we see we have a membrane bowing, and then we say, okay, in average, we do the same. We compare it as if it was a plate with a less displacement overall, but being a parallel plate displacement. This is the piston equivalent formulation. And it's just a simple comparison. If you had a silicon diaphragm, really a plate with some stress, 20 megapascal stress is a very low, is already a good low stress in a tiny diaphragm, 300 nanometer thin. And with this set, we generate this in 10 nanometers per Pascal easily. Yeah. If we want to achieve the same sensitivity with a plate, which is stress-free, it would be nearly 2 micrometer thick, this plate. And you see, we do a much thicker plate than a diaphragm to generate the same sensitivity. And if we were using the same set with a floating plate, we can generate this nearly 3 micrometer thick. It's easier to manufacture, but of course I could go the inverse way. I can say, okay, I keep maybe only 1 micrometer thin membrane. That allows me to reduce the clamped plate. It is only 300 or 600 micrometer diameter instead of 1 millimeter and generating the same compliance. And the chance of the floating plate, since it's more sensitive, I can make it much smaller to generate the same compliance. So only 400 micrometer in diameter. It is less than half the size of the circular membrane. Is this now the best one? This is the question, yeah. Of course, if you reduce the area of the transducer, we lose electrical sensitivity because the capacitance is getting smaller. So it is not such simple, but just part of the discussion and optimization. Yes, and this is a realistic situation of a diaphragm. So typically we have a mixed behavior of a diaphragm. We have a little bit plate behavior and a little bit membrane behavior. This is a membrane, in this case of 1 micrometer thickness. Okay, this was simulation for a squared membrane with different sizes and different stress in our material. So if, for example, we have this 1 millimeter diaphragm and we increase the stress, we have different domination here. At low frequencies, low stress, we see more or less this plate behavior. So in this area, the sensitivity, the compliance is independent of the stress, but then we come into a regime where it is depending on the stress and not so much on the size anymore. So we see basically that we have a plate behavior and then proportional to the area force, the compliance, and we have a membrane behavior inverse proportional to the stress that we apply. And then sensitivity, again, proportional to the area squared. So, and in between is a little bit from both worlds. Typically is not easy to come into this range of stresses. Typically we are in this range 10 to 100 megapascal, and then we can control quite good, but never completely give up about the compliance of the plate. Yeah, this is situation of membranes and plates. I have here some examples. This is how do we fabricate such a diaphragm? We can use all these different materials that we have in the fab. We have silicon, we have polysilicon, we have oxides, we have nitrides, and just from the fabrication, we know the different levels of stress. LPCVD nitron 1 gigapascal of stress. Of course, we could do a very high tension diaphragm, metallize it and use this as a membrane for the microphone, or we go to silicon or silicon on insulator with low stress levels. And this is simply a measurement of polysilicon diaphragms. And the polysilicon has a special way of fabricating it. So if, and the stress level finally depends on the implantation dose or on the conductivity of the diaphragm. Basically what you see in here, you can fabricate stressed membranes with some low doping. And if you increase the doping, you reduce the stress. This is favorable. So we want to go to this level, for example, 10 megapascal or 25 megapascal with some special implantation. But if we not control very well our electrical conductivity, we jump into a compressive situation. And compressive means the membrane will start buckling, and then we cannot control our sensitivity or gap anymore. Basically, it is very important to control the fabrication. And it is not only that the doping plays a role, but also temperature budget. So whenever you run through with your silicons through different process steps, oven steps where you apply 900 degrees Celsius or something like this, step by step, then you change the stress. Basically, the more temperature, the more the polysilicon is changing its nature and is going into stress direction. What we learn from here, you start developing of such a device in maybe a CMOS environment where everything is controlled for electrical parameters to get nice transistors. And now you use the same process to generate a specific mechanical nature of your device. First of all, you need to characterize because nothing is known. And that was a situation those times that you really try to find a space where you can control the mechanical parameters of your membrane or diaphragm materials. Of course, you can use the different layers and do combinations of those devices to get the right situation of your membrane. Okay, there's a lot of design or a lot of research on material parameters to get stress level controlled or whatsoever. Of course, you have also design chances or design limitations. What we see here is a set of different diaphragm designs, starting from the all-over clamped diaphragm. This is under tensile stress. Basically, this is the device which we used to characterize those material parameters. So a very simple circular clamped diaphragm under stress, so is a membrane. Then comes the idea we can relax some of the stress if we do slots into the membrane. So basically, this is 4 slots resulting into 4 arms that support the inner portion of the diaphragm. That relaxes part of the stress. We see a similar design from STMicroelectronics, a membrane hinged on 4 parts. A more advanced situation is here. So this membrane, the light color is the membrane supported at 16 arms. So this relaxes part of the stress in my device to get it softer. And what you see here in magenta is the counter electrode, which is simply below this electrode, in between is the gap. And then we have some other kind of spring supported membranes or diaphragm. You see here long arms to support a 1 millimeter diaphragm. The idea is that the diaphragm is moving like a piston up and down from these long arms. Or here from analog device again, you see a plate diaphragm with a long spring supporting the edge. So this is ways to design, and it's a very delicate design if you see this, and have made different approaches into application. So this is the idea. We have a given material and we design the sensitivity or compliance of the diaphragm by layouting it. It's just one of the measurements or characterization and simulations of diaphragms with circular clamping, and then you increase the number of, or that you make it softer by spring supporting until here you have narrow, only 4 support arms of your diaphragm. What you see here, if the circular has a 1 sensitivity, the next one has double, 3 times, 4 times, 5 times the sensitivity of simply this clamped membrane. And this is all fabricated with the same material parameter of diaphragm, just getting you different sensitivities by design. And there's limitations to it, of course. What you see in here from the color code already, that the edges of the diaphragm is open and it starts bending a little bit due to stress gradients. So not the highest sensitivity is necessarily the best one. Yeah, this is the bowing. If you have 1 arm of this and you simulate with an FEM program a certain stress level, we find that in this direction or in that direction, we have a little bowing about 100 to 300 nanometers of our 300 or 400 nanometer thin membrane. And the intrinsic stress is 30 megapascal of the diaphragm as measured, but the top side of the diaphragm, if you look from upwards, it has 20 megapascal, the bottom side has 40 megapascal, so it bends in itself a little bit. So this is not easy, this is realistic situations. And I have here a picture of such a membrane. We run up the voltage here. You see repeatedly, pull in at some 6 volts. You see then the membrane is hitting the counter electrode. We see this by optical means, yes, flattening out. And what you also see here is the bowing of the diaphragm. The edge is hanging free and is, yeah, not seeing so much this pull-in voltage. Interesting to show this, and was Michael Brauer, who did a PhD on this stuff. Yeah. Yet another way of relaxing stress. So we were relaxing stress by lateral design. curving out these springs and stuff like this. This is limited and usually also in conflict with the area overlap of the electrodes. Then comes the invention that we can relax stress also if we have a circular membrane and we put corrugations inside. Corrugations is rings with going up and down in Z direction. If you cut into here, you see in the tiny membrane with these corrugation rings. So this corrugation rings is kind of a spring structure in this direction. So if you have tensile stress, those arms will relax a little bit the stress in the layer and making the total device softer. So basically the string is relaxation. You can calculate this and finally find that the compliance of your device is in some sense proportional to the number of corrugation lines. So the more lines you do, the less, the more compliant it is. And the height of the corrugation is with a squared behavior. Of course, if I have here a high corrugation line, the lever, the arm, which is relaxing stress is higher, and this is a very effective effect. So we see here a 400 nanometer diaphragm with a 1 micrometer corrugation height, for example. And it is nice to show that, again, we have here the circular diaphragm, the spring diaphragm, and the same diaphragm with 4 or 8 rings inside the layer, corrugation rings, and it is scaling nicely with the number of rings. And this is finally also the chance for productive designs that nowadays use these corrugation rings to improve sensitivity. Yes, and I also attach a floating membrane device example here from the company Knowles. Knowles, you remember, that was the company who did first this microphone in the flip phone. And they invented very early this kind of a floating diaphragm. If you see here the wafer, you have a piece of silicon diaphragm, which is only 0.6 millimeter in diameter. As you remember, the smaller you can do it if you have a floating device. And there's a second electrode above this, and this plate is basically free. It's just having these anti-stiction dimples so that it not sticks to the wafer. And there's also posts and anti-sticking dimples in the top electrode. So if you switch on the voltage, the floating membrane hits first of all this anchor or these posts, but then it can slide. When it is moving, it can slide above this. These are the posts here. Is in a circumference, they are arranged, and this is then the tiny diaphragm, which is basically floating. If it is floating, how could you contact this? Of course, it is like a circular plate with one arm attached to the substrate. So this arm is also electrical connect to it. And this is a very successful MEMS device, a MEMS microphone device. Good. So we had a lot of situations, some more hints about business and success factors. I always like to show from what we know today, these are smartphones nowadays, and you know, the Infineon, they fabricate the wafers, the chips to it, and in between, that was finally very important to mention, is the companies that bring chips into packages and sell to the OEM smartphone or telephone manufacturers. Why is not Infineon directly selling to those in a package? If you look at those names, Hosiden, BSE, Goertek, AAC, this is traditional companies that did in the past these electret microphones. So in the early 2000 years, they were busy and having the whole market for microphones. When then some guy comes up and is delivering a new technology, they would have lost all their business. So they fight it against this silicon microphone tendency. And the very symbiotic solution finally was that Infineon was selling those guys, the silicon, they package into their capsules and packages, and they have still the good relationship to their OEMs. So this is a win-win situation for both worlds, and that was quite successful. By the way, this is a wafer of microphone chips. This 200 millimeter diameter, and I believe this 25,000 microphone chips on it. And this is the form factor. You have here, I hold a frame and the dicing foil, and we have the diced microphone wafer on this. And with this, you ship this to the packaging partners, and they pick the microphones into their package and stuff like this. We will see how to fabricate this later. And yeah, you see what this means if you have such a symbiotic business field. Nodes, the first one, does the packaging of microphones. They are sourcing the silicon of their own design from foundries. They had early 2006 nearly 100% of the market share. You see here Infineon was with the rest of the market share just coming in. And over the years, with a growing market, the shares benefited to Infineon, and of course Nodes gave a little bit up about this, while the total market was also increasing. That means the end customers, they always want to have more than a single source. At least there's two sources delivering into the market and some more. This was 2014 when Infineon had 34% market share and sold the first 1 billion MEMS in a year. You see in 2014, then the total market was something like 3 billion pieces. And yeah, we look at, this is a slide from November last year, which I got from Infineon. Then they were claiming they have 44% of market share and overtake the first one in the market, Nodes. And then there's a huge gap to others. So they are now technology leader in the market with different devices that we will see later on. And all in all, this is quite aggressive market at the moment. People are fighting for shares, and a lot of Asian-based suppliers try to get market shares as well, because you sell billions of those, and it's an attractive market for a MEMS device. Yes, okay. If you look again, we started today with Graham and Philip Reis and all those inventors that invented microphones. In this market report, they cite just Graham Bell with one of his speaker or microphones. And you see 19th century to 2000 is a long cycle of development from the 20s when they started the electrostatic to the 70s when we had this nice device, and the electrodes still till the year 2000 basically in the market. There's a long innovation cycle, so to say. And if you look then and compare the innovation cycle for the MEMS microphone, within 20 years, busting all the market and enabling new functionalities with multiple microphones in the phones or in your headsets. You have the phones as well. It's a very fast and steep innovation cycle enabled by technology. And of course, we can ask ourselves, will there be yet another innovation cycle? Can you do microphones maybe without micromechanics? I don't know. Those devices are all mechanical transducers, more or less. And it's a fascinating situation to see how fast innovation cycles nowadays run. Yeah, with this, I come to the end of the lecture today. I'm giving you an insight into historical developments of microphones, the general idea of transducing sound with a diaphragm and a referenced volume. We have so many ways of picking up then the displacement of diaphragms, but we concentrate first of all on capacitive transducers, starting with the early electric microphones. changing to the capacitive devices. They need a certain sensitivity out of an electrical and mechanical one. So basically, nowadays, bias voltage, air gap, and mechanical compliance are key parameters in our devices. We cannot discuss sensitivity without the bias limitation, the pull-in voltage, which is limiting capacitive transducers. And afterwards, we can really argue with technology specifications about the mechanical compliances of diaphragms. Yes, this is what I could share with you today. Thank you very much for joining this session. And I stop now recording. Wo ist das jetzt stoppen?